Hello and welcome to Aditya classes, and this is Manish Tamar. Today we are starting a new topic from Operation Research that is called sequencing. So before we get on with the method or approaches to sequence jobs, let us have a brief introduction of what sequencing is. Now if we take very simple example, what is sequencing? Let us take two very simple jobs that will be run on one machine each. So I have one machine and then I have two jobs, job A and job B. So if I have these two jobs, let's say they require 3 minutes and 7 minutes each. So what should be the sequence so that the complete discomfort is minimized for all the jobs? Suppose this was a service station, let us not call it a machine, let me call it service station. So if it were a service station, so what will be the best mechanism so as to minimize the waiting time for all the jobs, average waiting time? So what will be the best sequence? Now how do we ensure what is the best sequence? There were two options. You could have gone in with job A and then job B. What happens in this case? If you start at time 0, job A is finished in time 3. It takes 3 minutes. It may be 3 minutes, 3 hours, 3 days. So if we start at moment 0, job A will be completed in 3 minutes or 3 days or whatever it is. Then if we take job B after A, so B can start at 3. Why B can start at 3? Because our service station was busy. Our service station was busy serving A. Now when our service station is free from A, it has completed the task from 0 to 3. Now we can immediately start with B. So it starts at 3, it takes 7 minutes, it will be completed at 10. This is it. Now if we take a very small parameter, what was the waiting time? What was the waiting time for A? 0. 0 waiting time, because as soon as A arrived, it was started. It started serving at 0. We started serving at 0. So what was the waiting time for A? No waiting time. Then what was the waiting time for B? They arrived at the very starting of the day, at very starting of the calculation. So they arrived at moment 0, but B had to wait for 3 minutes. So what was the waiting time for B? It was 3 minutes. Why was it 3 minutes? Because A started first. Now because A started first, so A had to finish. It took 3 minutes to finish and then B started. So if we take, what is the total waiting time in such case? 3. If I go for average waiting time, 3 by 2 making it 1.5. 1.5 minutes, hours, days, whatever is your unit. So in such case, the waiting time was 1.5. Waiting time when sequence was AB. Let me see what is the waiting time when sequence is BA. If we take the sequence of BA, then what happens? First B and then A. B can start at moment 0. If it starts at moment 0, it will take 7 minutes, it will finish at 7. Then we can immediately start A. So A starts at 7. If A starts at 7, A will take 3 more minutes, it will end at 10. So in either case, I am finishing my task, I am finishing both the tasks at 10. As far as me being free is concerned, I am free by 10 minutes. But what about the customers? Customers, if we say, what was the waiting time in case of B and A? B had no waiting time, it started at 0 itself. What about waiting time of A? A had to wait for 7 minutes. It arrived at the very starting moment, but it was served only after 7 minutes. Why were we waiting for 7 minutes? Because B was operating, B was being served. So waiting time for sorry, waiting time for B in this case in sequence BA was 0, but waiting time for A in such case was 7. Total waiting time becomes 3. Average waiting time becomes 7 by 2, that is 3.5. Now, if we see here, what do we mean by sequencing? We had two tasks A and B. We had to sequence them in such a way that we could either optimize the utilization of machine or we could optimize the waiting time of the customers. As far as utilization of machine is concerned, we see that machine is engaged for 10 minutes. Whatever sequence we try, we could have tried AB or we could have tried BA. Either ways, the machine is engaged for 10 minutes and there is no waiting time, no idle time. Machine is occupied for 10 minutes. So, as far as machine is concerned, we are indifferent. But what about the waiting times, average waiting times? If we see in case of sequence AB, the average waiting time was only 1.5, whereas in case of sequence BA, average waiting time was 3.5. So, this will be the idea why we will be going in for sequencing. Why do we need a proper sequence? Now, this was a very simple case. We had only two tasks to serve to customers and we had only one service station. So, that was very easy to manage, that you have only two customers and one service station. Either it could be AB or it could be BA. It gets a bit more complicated if you have three customers A, B and C. If you have three customers A, B and C, it gets complicated. Why? The sequence could be A, B, C, or it could be A, C, B, or it could be B, A, C, or it could be B, C, A, or it could be C, A, B, or so these many combinations were possible. We will have to make each of the combinations and then we will have to calculate waiting times or machine idle times, machine waiting times, so things like that. So, it will get very complicated. We will have to see for 6 such scenarios. What if there were 2 machines? Things will get further complicated. So, when we study sequencing over here, we will try to sequence these kind of jobs. Now, what we will be trying to do is, we will try to sequence n jobs on 2 machines. It could be machines or workstations or service stations, as we may call it, but there will be jobs or customers who are here to be served and there will be machines or service stations or workstations or whatever where we will be serving them. So, there could be n jobs and 2 machines. First thing that we will be learning is n jobs, sequence n jobs. Here we had, if we look at this scenario, this was 2 jobs on 1 machine. What we will be learning here will be n jobs on 2 machines. Instead of 2 jobs on 1 machine, I will be learning n jobs, not 2, not 3, it could be n jobs specifically only on 2 machines. Then second thing that we will be looking at is n jobs on 3 machines. Third, we will be seeing n jobs on m machines. So, slowly we will be growing, progressing our span of discussion. We saw when you have 2 jobs for 1 machine, it is simple, either it could be AB or it could be BA. But as you move ahead from 2 to n, it could be 3, 4, 5, 6, n. As you move ahead, things get a little bit complicated. We checked for 3 machines, we saw for 3 machines, it will be so many alternatives, 6 alternatives. So, as you move to n, there can be unlimited alternatives, at least that much alternatives, which is practically not feasible for me to manage or sort or trying n number of combinations. So, we will try to find out some mechanism. We will find out that mechanism for sequencing n jobs on 2 machines, n jobs on 3 machines, n jobs on m machines. But yes, in these 3 cases, I will be putting up a condition. That condition would be that sequence of service is fixed. The condition would be that sequence of service is fixed. Sequence of service is fixed matlab, meaning you go on first machine, you go on second machine. So every job, you will be having n jobs coming in, but every single one of those will be going on first machine, then on second machines. None of these will be doing that. It needs first, second machine and then first machine. So there will be no second machine, first machine, rather it will be always first machine and second machine. So every job that walks into my workstation, works into my service station, it will first go on to first machine, then it will go on to second machine. So the sequence of service is fixed. The sequence cannot be changed. So this will be a limitation. But then if you have visited some service station, for example a car service station, there are multiple number of workstations. There is a painting, there is a denting, there is a cleaning, then there is tires, there could be engine and whatnot. So let us say we have 5 workstations in that service station, 5 workstations, 5 different workstations where different types of tasks are being performed at that car service station. Now not every car will be required to pass through A, B, C, D and E, because not every car needs denting and painting. Not every car needs cleaning. If I am having a starting trouble, probably I will be, my car will be visiting only the engine station or the battery station or the electronics station. So in that case, my car will not be going to the tire station, my car will not be going to the denting and painting station, my car will not be going to the cleaning station. So when we come to real life, generally what happens is, it is not necessary that everything moves from station 1 to station 2, machine 1 to machine 2. There could be random sequences. There could be a sequence of A, B, C, D and E. There could be a sequence of B, A, D, C, E. There could be a sequence of E, D, C, B, A. Anything is possible. In real life, things are a bit more complicated. So what we are trying to do over here is, we start with a simple approach. We checked a very simple scenario, 2 jobs on one machine, A, B or B, A. But then we saw if there are 3 jobs on one machine, it gets a bit more complicated. Now we are generalizing. Why talk of 3, why talk of 4, why not talk of n jobs? N jobs on 2 machines, n jobs on 3 machines. And finally, we will be talking of n jobs on m machine. So this is what we will be talking when sequence is fixed. But in real life, things could get more complicated, and that complication could be that the sequence is not fixed. If the sequence is not fixed, then what I do? In such case, what I will do is, I have my 4th case, which is sequencing n jobs on m machines, where sequence is not fixed. So this will be what we will try to achieve in this topic of sequencing for operation research. Fine. So sequencing of n jobs on 2 machines, sequencing of n jobs on 3 machines, sequencing of n jobs on m machines when sequence is fixed. And when sequence changes, we will try to sequence, sorry, it will not be n jobs on m machines, rather it will be 2 jobs on m machines. So this is what we will be trying to see, and the method that we will be using would be Johnson's algorithm or Johnson's method for sequencing. This is what we will be trying to use for the sequencing problems that we will be taking in the sessions to come. Now, before we could proceed with sequencing, exact sequencing questions, before we could actually proceed with exact sequencing questions, there are certain assumptions that we make when we are trying to sequence. Those assumptions go like this. The processing time on different machines are exactly known and independent of the order of the jobs in which they are processed. Processing times of all the jobs are known. Job A will need 3 minutes, as we saw in our example. Job B will need 7 minutes. I know what are the times that they will take. I exactly know when someone calls me for service, what is the exact time that it will consume. I know the times exactly. And also these times are independent of the order, as we saw in our example. If you go AB, 3 minutes for A, 7 minutes for B. If you go BA, 7 minutes for B, 3 minutes for A. So it is the time required is very well known, 3 minutes and 7 minutes, and it is independent of sequence. If you go AB or you go BA, either ways it will be 3-7 or 7-3. So a total of 10 minutes of processing will be required. So the first assumption is the processing time on different machines are exactly known and are independent of the order in which the jobs come. So this is an assumption that we will be making for the Johnson's method or algorithm, for which we will be using for sequencing. So this is our first assumption. Then there is the time taken by the job in moving from one machine to another machine is negligible. So the switching time, the setup time, job A being removed from machine A, B being planted over there, A moving from machine 1 to machine 2, B moving from machine 2 to machine 3. So all these changeover times, setup times are negligible. We will assume that as soon as one task is finished, immediately you can replace with the other task. As we saw in our example where we were consuming time 0 to 3 for A, and then immediately from 3 to 10 it was B. It was not like 3.5 because I am unmounting A, then I am mounting B. We are assuming that those times are negligible. So we say the time taken by job in moving from one machine to other will be negligible. Time taken by job moving from one machine to other or job changings, unmounting one, mounting the other, that is also negligible. So those times are negligible. The switching times are negligible either for machines or jobs. So first assumption was processing time of different machines are exactly known and they are independent of sequence, 3773. Second is the time for moving, the time taken by the job in moving from one machine to other is negligible, 0 to 3, 3 to 10. And if there were a second machine, I would have switched A from first machine to second machine, 0 to 3 on first machine and 3 to whatever time is required on second machine. So switching times are negligible. Then there is another assumption, third assumption, which says once a job has begun on a machine, it must be completed before another job can start on the same machine. That is a logical assumption that if I start with one job, I will finish that job. It will not so happen that A needed 3 minutes of processing, I process it for 2 minutes, then I remove it, then I start working on B. That will not happen. If you start a job, you complete that job. So that is a logical assumption. Then all jobs are known and ready for processing before the period under consideration becomes. That again is a logical assumption that all jobs are known and are ready for processing before the period for consideration begins. Whenever I am there to consider, should I go with job E or should I go with job F, I will assume that E and F are available over there. Fine. E and F may not be available in the beginning when I started calculation, but whenever need arises for next job, E is also there, F is also there, you can pick whichever is best according to your Johnson's rule, jobium, which we will see. Fine. So all jobs are known and ready for processing before the period for consideration begins. Whenever a job is ready for sequencing, whenever a job is ready to be put on machine, whenever a machine is ready to pick up a job, I assume that the job is available. It is not so that fifth machine is idle, sitting idle, and there is no job, and then 10 minutes hence a job comes. This is not the case. If a machine is idle, if a job needs processing, it will be mounted. So it is available when the need arises, when the consideration begins for sequencing. Then we have fifth assumption, which says only one job can be processed on a given machine at a time. Obviously, first machine was processing only job A, 0 to 3. It is not so that it is processing 0 to A also and B also. From 0 to 3 it will process A, from 0 to 7 it will process B. It is not possible. 0 to 3 it will process A, then 3 to 10 it will process B. Or in other case, it would process 0 to 7 B and then 7 to 10 would be A. So, multiple processings are not allowed, not possible. That again is a fair assumption. So, these assumptions are not such that which are unbelievable. But then we should lay down some ground rules before we could proceed with some algorithm, with some procedure, with some scientific procedure. Only one job can be processed on a given machine at a time. Machines to be used are of different types. Again a logical assumption, whatever machines we are going to use, they should be of different types, because if all were similar, we could have used all of them in a go. Why wait for machine 1 to be free? You could have mounted the job on machine 5. So, that is also an assumption that all machines are different, all processings are different, and if a job needs machine 5, it needs machine 5. It is not so that it can work on machine 1 also. So, machines to be used are of different type. The order of completion of jobs are independent of sequence of jobs. The order of completion of jobs are independent of sequence of jobs. The order in which these are completed is independent of the sequence in which they arrive. Why is it independent or different? Because my sequencing will be based on Johnson's rule. I might pick up, let us say the arrival of jobs is A, C and B. Jobs arrive at, 3 cars arrive at A, C and B. But now when I start processing, I realize that A, C and B is not a good idea. I will go with B, A and C. So, I have changed the sequence. So, the sequence of their arrivals and sequence of their service will be independent. This is the assumption. The order of completion of jobs when they are being completed is independent of when they are arriving. So, these are certain assumptions that we'll make before we proceed with our sequencing. So, that was it for opening session on sequencing, introduction of sequencing. Thanks for watching. Bye-bye.